Boats. They transport things, people, animals, etc. There are sailboats, dinghy boats, houseboats, jet boats, lifeboats, motor yacht boats, canoes. Game boats, trawler boats, runabout boats, ski boats, banana boats, fishing boats, and yeah, you get the idea. For this presentation, I will be constructing a miniature paddle boat powered by a rubber band. The first two principles that play a part in boats and anything that floats or sinks are displacement and buoyancy. When you put something in water, the water level rises depending on the mass. How liquids move about based on the volume of objects inside them is known as displacement. The upward force that objects feel whenever partially or fully submerged into water is buoyancy. Whenever objects become fully immersed, they experience enough buoyancy to reduce their weight. Think of how it's easier to move when swimming, or how it takes much less effort to lift something out of the water than the same object on dry land. Buoyancy and displacement correlate together. The amount of displacement an object equates is equivalent to how much buoyancy it receives. The concept is known as the Archimedes principle, and it's part of why some objects float and others do not. Two objects can weigh the same but behave very differently in the water. One may float, another may part way submerged in the surface, and one more may sink. The same applies to objects that are the same in volume. Density equals mass divided by volume. If you have two objects with the same volume, but one weighs more, that heavier one will be denser. And while specific parts of a cargo ship or powerboat may be incredibly dense and others are not, the average density will impact if an object or ship floats. We use steel and other dense metals in the construction of boats all the time, and they still float. This result is because the other materials on the ship, along with the air inside, help balance out the average density to a level that it can stay afloat. The calculations can get a little bit complex when you're unfamiliar with all the values. They involve comparing the overall volume and density of an object to the amount of water it displaces, as well as how much buoyancy pressure that displacement will produce at a certain depth in the water. By calculating these values, it's possible to determine if a boat will displace enough water to provide enough buoyancy to keep its maximum density afloat. Manufacturers use these types of calculations to learn not just if a vessel will work, no matter if it's an outboard motor vessel or a sailboat, but also its maximum carrying capacity, crucial for large cargo vessels that transport massive amounts of weight along with them.
Look what I got. I got a jar of dirt. I got a jar of dirt. And guess what's inside it?
Enough!
The materials needed for construction of the paddle boat are 25 to 50 popsicle sticks, preferably the larger kind, a hot glue gun, hot glue, 2 identically sized bottle caps, 1 skewer, at least 1 average sized rubber band, get extra in case it breaks, 1 safety pin, a small ruler, a drill, caulking, a screwdriver or something to poke a hole through the bottle caps, scissors or tweezers, and 1 box knife, as well as a writing utensil like a pen or marker to mark where you will cut certain popsicle sticks.
Don't touch the Nemo!
He touched the butt.
With 4 popsicle sticks, line them up like this. Next, mark a popsicle stick at length to fit across those other sticks. Cut it down to the size with the box knife. Make 2 others just like that one and glue them down. Next, mark out the front of the boat and cut it down to size. Then make some sides. Mark the length and mark the ends rather pointed or slanted. Glue them on and do the same with the 2 front pieces. Then make a back piece. After you've glued those all in place, make 2 pieces. One that fits at the front length of the boat and the other that slides into the front. Don't glue them yet though. Cut out 2 top pieces of the popsicle sticks and glue them on the front piece. Cut out little shapes like this as well on each of the pieces. Next, drill a hole through the front piece. This was the hardest part for me as one of the little tops kept breaking. Next, glue the 2 pieces in front near the front of the boat. Then make 1 long piece for the length of the rest of the boat and place it in for strength. Also make 2 other little pieces next to the sides. Then start the tedious work of taking off the 3 pieces you glued on the bottom at the start. I did not actually break the boat. I was very impressed with that, but it probably took more than 30 minutes to get them off. After that, I cut off the back pieces. Cutting off these pieces on the bottom of the boat and at the back will minimize any drag the boat still possesses. Next, measure the sides and mark a hole at the same distance, preferably more towards the back of the boat. Also, make sure the skewer is high enough from the bottom because the safety pin that will go in the future could interfere with the spin of the paddles if not high enough. Inside the boat, reinforce the sides with another stick on each side. Then drill a hole big enough for a skewer to fit through. Afterwards, poke a hole through the middle of the boat and bottle caps in which the skewer can also fit inside. Then cut out 8 paddles. Then slit the bottle caps 4 times. Cut off the top of the skewer, insert the paddles, and glue them together. Insert the skewer through the boat and cut it down to size. While putting on the other paddles, make sure they are in sync with the other bottle cap. Glue on the rest of the paddles and make sure nothing is interfering with the spin of the wheels. Next, cut off the top part of the safety pin and insert the sharp end into the middle of the skewer. Make sure as it spins it does not hit the bottom of the boat. Put a rubber band through the little hole at the front. Then put the rubber band on the safety pin and wind it up. If it is working well, put some caulking on the boat to seal up any holes. The boat is now ready for testing.
I have to find the boat.
A boat? Hey, I've seen a boat.
You have?
Uh-huh, and it passed by not too long ago.
A white one?
Hi, I'm Dory.
For this experiment, I went to my grandmother's pool. No current was on in the pool, and there was a mild breeze. Okay, and make sure it floats.
Okay, it floats.
Yeah! First try to make it move. So we attach it to the little pin here, and we wind it up. Yeah, we're gonna let it slide. Alright, ready? Set. Go.
It works. Look at that. It's beautiful. Of course, it's out in the middle of the water.
Yay! That's pretty far. 3, 2, 1, go. Yeah! The boat worked twice. It got about the same distance both times. The way it is built slightly slanted and the wind caused it to curve. But unfortunately... Yeah, the water caused the sticks to start to collapse on themselves. We let it dry out for a while, but the wheels still wouldn't fully turn. We added some Vaseline in the skewer, and I cut some of the sides down, but that still wasn't completely enough. We tried letting it go again, but I cut the sides down a little too much, making holes that let the water flow in the boat, causing it to sink. The main flaw is definitely the design. The whole boat is crooked, including the paddles, which makes the boat vulnerable to clog itself.
This is either madness or brilliance.
It's remarkable how often those two traits coincide.
The motion of a paddle wheel boat will obey the law of conservation of momentum. As the paddles push the water in the backward direction, the boat would be propelled forward. An efficient paddle wheel would be one that translates into maximum forward motion for a particular amount of energy spent. When you wind up the paddle, the rubber band stores energy. This is potential energy, which occurs because the twisted rubber band is not in equilibrium. You have to hold it in place or it will unwind. When you let go of the paddle, the rubber band unwinds to rotate the paddle and push the boat forward. That unwinding is the conversion of potential energy to kinetic energy, which is the energy of motion. The rubber band moving the paddle and the paddle pushing on the water and the boat moving forward are all examples of kinetic energy.